Hello, welcome to the course on power electronics with wide bandgap devices. Today I'll continue the discussion on EMI. In the last lecture I have already discussed about different types of EMI. So as I have discussed in the last class, so the EMI we have seen we can actually classify in two types, right? So conduction mode EMI or conductive type EMI, and then radiative EMI. Now, in this also, there are two different types of EMIs in conductive type. One is common mode or CM, which I have represented in the last lecture. And differential mode. In radiative also there are different categories that we have already discussed, so that inter different types of radiative EMI can be present. But today I'll be focusing on conductive type of EMIs and then how it is coming. So if you see in power converter, so basically any power converter, there will be power supply first, right? So it can be any type of supply, DC, AC, any type of power supply can be present. So power supply, it is connected to the power converter. Again, the power converter can be anything, AC to DC, DC to DC, or DC to AC, or AC to AC can also be present, right? So we can just say power converter or the equipment under test. Either power converter or equipment under test. So we have to check whether this power converter is getting affected by the EMI noise, either conductive or radiative. So if it is so, then we have to provide the solution. Before measuring this EMI, we have to first understand what are the EMIs that can be present in the power converter. So that is what I am going to discuss today. So then this power converter will be connected to some load, right? So this is the basic structure of any power electronics system. So again, load can be AC, DC, anything, and power supply can be AC, DC. Power converter can be any type of conversion. So if you see here, so this is in this particular system, ideally this system should operate properly, but in normal operation what happens, so there will be EMI present due to radiative in this power converter, right? Radiative kind of EMI. So this is the radiative noise. Okay, now again there can be some parasitic component to be present in the path. What are those parasitic components? One component is the parasitic capacitance. So this capacitance will be connected to the protective ground. So I can just make this protective ground common for all the parasitic capacitance. So this is protective ground This one is basically, you can say, this is the circuit ground. Then circuit ground and the protective ground, they are different. So between circuit ground and the protective ground, there will be parasitic capacitance, which will cause this EMI to be present in the converter. So now this parasitic capacitance will cause presence of this is the reason for common mode noise, or I can just say conductive noise. So the reason why this noises, radiative or the conductive, any EMI noise is become very significant in high frequency is due to DVDT and DIDT. So like when we are actually considering wide bandgap devices, so basically for wide bandgap devices, any device, whenever we are considering silicon carbide or gallium nitride, the one of the important thing is that this converter should be able to operate at high frequency. Now if it is operating at high frequency, then what will happen? The rate of change of voltage and the rate of change of current will also be higher. Means this dVdt and didt during switching will also become higher. T will be very small for very high frequency operation. That will cause this components to be very high, and this will cause higher value of EMI noise to be present during switching, will cause EMI noise through the parasitic inductance and the parasitic capacitance. Now this green capacitances which I have shown here in this block diagram, these are parasitic capacitances, right? So now these capacitances are not present in the circuit, but it will be there in any converter with respect to the protective ground. If the frequency is higher, then this component becomes quite significant through the parasitic. This will be inductance and capacitance. Okay. Components. Now, if this dPdt and didt are present, so basically what happens? If dVdt is present, C dVdt will cause current to flow in the system. That is parasitic, like dVdt with respect to the parasitic capacitance, that will cause this noise to be present. So basically if I try to quantify this DM noise and the CM noise, so DM is with respect to differential mode and CM is with respect to the common mode. So then DM noise it is basically current driven noise. Right, this is current driven noise. Why it is current driven noise? Because when we are saying DM noise, so basically what will happen due to change of current means didt. So current driven noise, it is coming due to the di dt. So L di by dt will cause this noise to be present, right? So basically this is why it is called current driven noise, and this is due to, this is actually due to the presence of magnetic field, means this L is basically not the actual inductor, so I can just represent this as LP. So in terms of like parasitic inductance, so this is due to the magnetic field. Again, this magnetic field is not actual inductor or the transformer which we are considering in the converter. This is parasitic magnetics, parasitic inductance which is present in the circuit. Now, due to low impedance, path. Okay, so basically if there is a magnetic field and if also there is a chance of low impedance, will cause higher value of didt, and then higher value of didt with respect to the magnetic field, it will cause higher value of dm noise to be present. Okay, now similarly if I try to quantify this cm noise, so this CM noise, it is known as voltage driven noise. So voltage driven noise, I am saying, so that is with respect to the dVdt. So this parasitic capacitance, so I can also represent this capacitances as Cp in order to make it clear that these are parasitic capacitances. So this Cp with respect to this dV dt will cause this CM noise to be present, right? Now this is due to the fact that there is electric field. So when I am saying electric field, so what happens? So you can understand if there is a ground, so basically circuit ground and the protective ground or the actual ground, if they are different, then what will happen? There will be electric field between these two grounds, and this will cause parasitic capacitance to be present, and this electric field will cause the basically CM noise to be present. Okay, so and electric field and also high impedance. Okay, so you can understand with respect to capacitance, so this is coming as high impedance, and inductance it is coming as low impedance. The current will be higher, and here the voltage change will be higher, rate of change of voltage will be higher. So these are the reasons for this CM and DM noises. Now if I have to identify these noises in circuit, so then let's see how this is going to be. So let's consider example of an buck converter. So buck converter is the simple power electronics converter. So in this, so let me just draw the circuit diagram of the buck converter, then I can show that how this CM noise and DM noise will be in that particular converter. So with respect to buck converter, so you can see here, so this is the input voltage of the buck converter, the input capacitance of the buck converter. This is connected, like if there is any like distance between V in and C in or the converter, so this capacitance is present to make sure that there will be constant supply from the input. Okay, now this is connected to, let's say, switch S1, and then in place of diode I'm just drawing another switch S2. Then there will be the inductor L and the output capacitor C0 of the buck converter, and this is connected to the output load. Let's say the load is this, so any kind of load it can be, so just representing it with like this. This is C out, right? Now ideally this converter should not have any other component, right? But in practical scenario, what will happen? There will be different parasitic capacitance. Sorry, I'll just use different color. So for the parasitic component. So this parasitic capacitance to be present. So let's say this is CP1, CP2. These all are parasitic capacitances, but the values with respect to different point of the circuit, it will be different. So that is why I'm just representing it in terms of 1, 2 like this. And then again there will be like parasitic capacitances from here to, let's say, ground. And again there will be point. Okay. So now these all are connected to the protective ground. CP3, CP4. Now if you see here, so then basically the common mode and the differential mode current we can actually figure out. So let's consider this differential mode noise. I am just representing in red color, right? So it will be in the similar direction as the power signal. So generally what happens, the power signal, it goes from the input through the switches to either like switch S2 or maybe through L to the output capacitor, right? So this is the direction of the current, and the return path will be through the circuit ground, and this will be the direction of the current. So it will be, sometime it will be through this inductor and the capacitor, and sometime it can be like this also. So this is how generally this differential mode current path will be. It will be along with the power line, power signal line. Now when I try to represent the common mode noise, so common mode noise will be in the similar direction. Differential mode noise, it will be in opposite direction. You can see here, so this like positive of the differential mode and the negative return path, they are in the opposite direction. If you check the arrows, they are in the opposite direction. But in case of common mode noise, they will be in the similar direction. So let me just use different color. So this yellow is visible. So if I try to represent in this color, yellow color, so then the current will be, so it will come from this, you know, like this is due to this electric field. So this is basically voltage driven noise. So then it will come from this parasitic capacitance says stability. Okay. So this is the parasitic capacitance noise. So it will come from this particular path. It will flow along with this. Okay, one will come from this. Another, since there is a parasitic capacitance, it is connected here in this path, so it will go in this direction. Hopefully this is visible to you. This will go in this direction. Right. Again, there is another capacitor CP3 and CP4 are there. So basically it will have return path through that. So basically any of this like CP3 or CP4, it will be like provide the, so this is actually this will provide return path. So just so it will provide return path for this. This is the return path, and then the upper capacitor which is connected, this CP3, it will provide a return path through this. So you can now check. So basically arrows, you can just see how these arrows are connected, right? So this will provide return path for different current. So you can check here. So the positive and negative current of this this is common mode. So just representing the common mode in yellow color and then differential mode in the red color. So differential, this is common mode noise, noise path, and then this is differential mode noise path. So if I try to represent these two different current of the differential mode, so basically IDM1, so IDM1 here in the, like when it is going forward, and then IDM2, so they are basically opposite, means IDM1 and IDM2 are having different sign, different arrow. And similarly, if I try to represent this ICM1 and ICM2, they are in the similar direction. So that is the difference between differential mode and the common mode noise. Okay, so you can check here the return path of this differential mode and common mode noises are also shown here. So this will return through this path. So you can check. So this is this one, like whatever is going in the forward, we can say this is like CM1, and then whatever are coming in the return, this is like, you can check like this will be of similar magnitudes, ICM1 plus ICM2. So it will be having ICM1 plus ICM2. So basically IDM1 will be equal to IDM2, but sign will be different. Whereas the return current, so basically ICM1 plus ICM2 will provide the return path current, and the similarly ICM1 and ICM2, it will be through the two different power lines, this positive and the negative lines, right? So they will be of different, they can be of different magnitude or maybe similar. So maybe also basically this ICM1 and ICM2 relation, if I want to establish, so then it may not be similar. So basically ICM1 ICM1 and ICM2, they may be equal or may not be equal. So this relationship is depending upon the parasitic capacitance values. Okay. So now this is with respect to the buck converter. Similarly, this path can be represented for any other converter. Means like this EMI noise path, conductive kind of EMI noise. So this is like common mode and the differential. These two different types of EMI noise. In the converter, we can analyze by actually finding out the parasitic component values and how this DIDT and DVDT of the converter switches is going to be. From there we can analyze what will be the values of the CM and the DM noise. Just to give the example of another converter, so I am also considering another boost converter so that it will become clear to you. It is the similar to the buck converter, exactly similar. So I'll just draw the circuit diagram. So then the all type of, generally the converter either will be boost or the buck, so then it will be clear for all kinds of converter. So again it will be having input capacitor similar to the buck converter, right? Here inductor is present at the input in the boost converter. So there, here the same type of switch S1, and then there is a switch S2 which is connected to output capacitor C out, right? Now this is connected to the load. Okay, so this is also having similar type of situation. So basically it will be having DM and the CM noise. So now if I have to provide the parasitic capacitance path, it will be also similar. So I am using same color just to make sure that, you can just connect these two diagram. So it will be also having this, like with respect to this particular switch there will be a parasitic capacitance like this, and similarly one another parasitic. So this is CP1, CP2, CP3, CP4, right? Now similar font color if I use, so basically line color, then DM noise path will be through this with respect to the power signal. So one DM1 will be in this direction and DM2 will be in this direction. So it will complete the path like this. So it will be having this path on this path, and here it will be having this path, right? So this is with respect to DM noise, and similarly the CM noise, it is connected like this. So it will go like this, and through this capacitance it will be having return path. Similarly in this one it will go like this. So just it will go like this. So basically through this capacitance it will be having return path. So we just connect this return path. So here the direction of ICM1 and ICM2, it will be in the similar direction. So you can check here IDM1, IDM2, and then similarly you can check here ICM1, ICM2. So these two currents are of same direction. So IDM1 and IDM2 you can check, and ICM1 and ICM2. This will be the path for common mode and the differential mode noises. Okay. So now I'll just so here noise current flows in power lines in opposite directions. That you can already see. IDM and IDM1 and 2, they are in the opposite direction. And CM, we can say noise current flows in power lines in same directions. That you can see with respect to ICM1 and ICM2. ICM1 and 2. Okay, so these are the noises which you needed to know with respect to the conductive EMI. Okay, so now if I try to analyze these noises, so then how I can analyze? So I can just draw the block diagram again. And then this is the converter with load I am drawing now, or the equipment under test. I will just write converter, so then it will be easier for you to connect. Right. So now this power source is connected to the converter. Now you have already seen the path for the differential mode and the differential mode path will be like this. And with respect to the ground line, so then the common mode path will be like this. So I'll just define this is not a problem. Right. So if I try to, so if I consider this current from this power source, so basically there are 2 points, so positive and the negative. If I consider this is the positive point and this is the negative point, and current from the positive point if I consider ip, and current from the negative point if I consider in. So the net current in each line I'll be getting as ip is basically summation of common mode and the differential mode current, because they are in the same direction. So basically ICM plus IDM, right? Now IN is basically difference between ICM minus IDM. So power line I am just now representing positive and the negative line. So whatever is connect providing forward path, that I am considering as positive line, and that current with respect to that particular line I am considering IP, and the return path I am considering as negative line, which I am representing in terms of IN. This can be anything, like with respect to AC source also it can be there, just considering these two lines as P and N, that it doesn't have to be only DC source, right? So now this positive negative currents we are getting. Now if I have to, now if you see this current, so this ground current, if I try to find out this ground current, basically, so the ground line I'm considering as like current with respect to ground line G. So this line I'm representing as G. So the current in the ground line will be 2 ICM. That you can understand. So basically positive line and negative line, both direction common mode current is flowing in the same direction. So the twice of this each line current will be going to the ground, or the summation of positive and the negative line current will be going to the ground. So in this case we are considering in positive and the negative line same currents are flowing, so that is why I am representing the with same current ICM, and this twice ICM will be going to the ground line. Okay, now this, if I try to like these equations, these three equations, so if I say 1 and 2 and 3, if I solve this 1 and 2, then what I will get? ICM equal to IP plus IN divided by 2, right? And then similarly IDM I will be getting as IP minus IN divided by 2, right? So then similarly this is with respect to the current I am getting. Now if I want to find out the voltage, common mode voltage, ultimately then what I will get? VCM also I will be getting similarly as VP plus Vn divided by 2, right? Similarly the VDM will be Vp minus Vn. So now you can see from this particular thing, so common mode current and voltage, we are, sorry, this is differential mode and this is common mode. This is with respect to common mode and this is differential mode. So this voltage and current we can get from any converter. So whether it is buck converter, boost converter, so this relationship we can find out, because we will be having the information of IP and IN, VP and VN. So then we can find out what can be the noises, the value of the current of and voltage of the noises in the particular converter. Okay. Now how these noises generally looks like? So basically if you see any converter, so with respect to differential mode, it is the same current which is flowing in the circuit. See here in the boost converter, if you check, so the boost converter, the switches, whatever current it is flowing, the same current will be flowing in the differential mode noise. So the shape of the differential mode noise, so it is basically, if I try to draw the equivalent diagram, so then power line, so it is flowing through the switches for boost converter, right? So this kind of noises are present. So then the noise will be similar, so like switch on and off will be there. So remember, these noises are due to the switching operation. So then when the switch is on, the inductor current, whatever it will be, let's say I am considering the continuous kind of current operation, so then this current will be there in DM, in this particular noise path, right? Switch on and off, it is going to be like this. So noise shape, it will be kind of like this, similar to the inductor current. Only thing is that in the negative side it will be 0. So this is the shape of the DM noises. And if I consider the CM noises, so CM noises is going to be a bit different, because if I try to consider the same equivalent circuit, you remember this, like there is a point which is connected from this to the ground. So then with respect to that, so the switching signal whatever is coming, so this coming with respect to, just a minute, the equivalent diagram will have, so this switch signal will be there, and then there will be parasitic capacitance path. So it will be kind of flat topped kind of signal will be getting. So this flat topped kind of signal will be getting in this kind of CM noise, and that we need to measure with respect to the particular converter, right? So here we can get mostly trapezoidal kind of signal, and here we can get mostly flat topped kind of signal with respect to its switching. Now these noises, how to measure these noises, or what are the steps we need to follow now? So now you know about these different noises. Now what to do with these noises? So what steps we need to follow in order to analyze these EMI noises? Basically, first we need to see what are the noises present. So the step 1, EMI design. So basically if I say step 1, we have to find out what are the different noises. So basically measurement and separation of CM and DM noises. We have to measure, we have to separate. Step 2. Now you know about different noises. You can separate out these noises, but first we have to measure. We have to know how to measure. Then if we measure, then the step 2, what it will be? Once we have the information, then we have to calculate the desired attenuation for CM component. We have separated CM and DM. Now we have to see whether the CM noise within the specified limit or not. The limit I will be discussing, like what are the limits that is provided for EMI. So we have to check these noises within the limit or not. If it is within the limit, then it is fine. If it is not within the limit, then what we have to do? Then we have to follow the step 3, CEM filter design, filter parameter. So we have to design filter for CM noise. So we will be designing filter for CM. Now step 3, it is for CM part. Step 4 will be, now we have to check for DM as well, right? Similarly calculate the desired attenuation for DM component. Similarly to the step 2 for DM, right? Now step 5, similarly we have to see if it is within the limit or not. If it is not, then we have to design DM filter. DM filter parameter calculation. Now this process we have to check, like by connecting filter in the system, we have to see the noises are attenuated to the desired level or not. If it is not, then what we have to do, we have to again follow the same procedure, again measure, and then we have to see that how much filter is required. Then we have to change the filter parameter value, and then we have to check again. This is, and then end. So these are the 5 steps. So this is for the DM part, and this is for the CM part. Okay, fine. First, we have to find out CM and DM noises. That also you know from the circuit. But how to measure these noises? So this is like the first step. Probably we need to see what are the measurement procedure for different noises, because you know these noises, as you have seen. So this will be in the very high frequency level. So in the megahertz and gigahertz, in that particular level. So then what we need to do in order to find out these noises, for because you know normal oscilloscope, it will not give you these noises, right? So then, and also like we need a setup to find out these different noises. So that is why the first step will be the measurement. Right. When I say measurement of the noises, so then how we have to do? So basically, this till now you have seen the power sources, it is connected to the converter. It is connected to the converter. Here, in between power source and converter, there will be one network which will be connected to measure these different noises. What is this network? That is known as LISN, or line impedance stabilized network, or known as LISN. So this network we have to place in between power sources and the converter. This network when we are placing, so then it will provide us values of common mode and the differential mode noises. Basically noises we can get, and then from there we can actually separate out, or we can separate out in the experiment itself. First let's see that what this network is and how this network can provide us different noises, right? So this LISN can also be like single or dual. So if it is single, so then generally it will be connected to any of the lines, like either positive or the negative and ground. And if it is dual, then it will be connected to both the lines and ground, right? So basically the block diagram of LISN is such that, so if it is single, then positive ground and the converter, positive P and ground G. Similarly, for the power source, P, and then this is connected to plus and negative, and then it is connected to G. So this is the ZP, so impedance with respect to the positive point. So this is single LISN. If it is dual LISN, so then it will be there will be positive, there will be negative, there will be ground, and then it will be connected to the converter. Then this is ZP, this is, let's say this is VP. VP, it is connected to ground. Similarly, there will be negative point minus plus Vn, which will be connected again this particular point through Zn to be connected to ground, right? So this is how this dual LISN, so this is dual LISN block diagram looks like. Now this LISN, again, like if we have to use it for different noises, means there are like two different points, measurement and separation. So we also need to separate this DM and CM noise, because filter for these two noises are different. One is current driven, one is voltage driven. Then the filter requirement, one will be capacitor, another will be inductor. So that is why we need to separate out, so that we can design the filter accordingly, right? So then for separation also, there are actually different kind of method people can use. So I'll just tell you about like two methods using LISN. If we want to separate out, so separation of noise. So using LISN, if we want to separate out, so the diagram, so basically configuration of the network should be like this. So I have shown you the dual LISN, how it is connected. So this is the dual LISN. We need dual LISN for separation, right? Then we'll have complete information of CM and DM noises. So then it will be connected to this particular point, and then this is one impedance will be connected here between this point. So this is Vn and this is Vp. So again one impedance will be connected here. This will be connected to the this will be connected again to one transformer. this will be attenuated at 50 ohm resistance. Okay, this is grounded. Now you can see here this is Vn. These points, so basically here 2 points are there. So here the switch can be connected like this or this, means this is 1, 2. Similarly this will be connected like this, right? Or maybe it can be connected like this, 1 or 2 point. So now this point, so this point can be connected to 1 or 2. Similarly this point can be connected to 1 and 2. Maybe I can just write this as 3, 4, so then it okay, fine, no problem. So basically I can just write here T1 and T2. So T1 can be connected to 1, 2 of T3, and then T2 can be connected to 1, 2 of T4. So wherever, so like basically these 2 points will tell you, so basically different points. So when T1 is connected to 1, just a minute, there is three, 4. So T1 can be connected to 0.1 or 0.3. Similarly, T2 can be connected to 0.4, and here it will be 0.2. So if you can't see it properly, I'll just highlight this is 1, this is 2, and with respect to this is 3 and this is 4. 3, 4 are with respect to T4, and T3 with respect to T3. This T3 points are, T3 has 2 points, 1 and 2, and T4 has 2 points, 3 and 4. Sometimes the T1 can be connected to 1 and sometimes it can be connected to 3. So means sometimes it can be connected to T3, sometimes it can be connected to T4. When it is connected to 1, that is connected to T3. When it is connected to 3, then it can be connected to T4. Now similarly, T2 can be connected to 4. So in that time it is connected to T4, and then when it is connected to 2, so that time it will be connected to T3. So both can be connected to both points. So in order to measure these two different noises, so one is that, so T1 can be connected to 1 and T2 can be connected to 4. The similar way, like that connection can be changed in order to find out the other noises. So that way this CM and DM noises can be separately find out by changing this switching position through the LISN network. So that is the network if we want to use for separation. So this is how we can actually find out two different noises, right? If we don't want to use LISN network to provide, so for that what we have to do, we have to provide this different network connection. If we don't want to do that, we can also finding out from the probe. So by using probe, if we want to find out, then what we have to do, we have to use similarly dual LISN. There we don't need this different network. We have to use dual LISN, that is for sure. So then one CM noise, for CM noise what we can do, these two lines we can just check the probe, we can connect this way, because you know this current are flowing in the similar direction. So then if we try to connect the probe this way, then this probe connection will give us actually voltage equivalent to 2 ICM. right? Now this probe, if we try to connect it with different way, so if we twist it here like this, and then if we measure the current here, so then here this will give us the voltage which is equivalent to 2 IDM, right? Now this is how this noise can be find out by measuring separately. So here we can find out, so basically voltages we can see in the probe. So this voltage which will be equivalent to this current levels. So again we can use this same in the equation in order to find out like different current, and then we can design the filter. And the using LISN already you know how to find it. So these are the different methods what we have to follow. So now you know about how we have to use LISN, and you like we have to separate the noises and everything. So how this LISN looks like? So till now I haven't told you about LISN network. So what this LISN network consists of? So it must be having some network configuration, some resistance, capacitance, all these things. So basically, if I consider single LISN, so then it looks like, so it is having, so if I consider LISN of 50 microhenry, so then it is having inductance which is of 50 microhenry. But this is not the only parameter which it is having. It is also having capacitor which is of 1 microfarad. Now it can be connected to very small value of resistance here, or maybe it can be directly connected to ground. Actual ground, not the circuit ground. So it can be connected to ground like this. Now here another capacitance will be there, which is generally of 0.1 microfarad, and this will be connected to very high value of resistances which will be of 1 kilo ohm. So here if I have to connect a resistance in series with 1 microfarad, it will be around 1-2 ohm, but with 0.1 microfarad it will be 1 kilo ohm. Now this point will be connected to the analyzer which is having 50 ohm attenuation. So to 50 ohm termination, which you have already seen in the previous, here at the output, here you can see where the 50 ohm termination is shown. So now this 50 ohm termination, it will be connected, which will go to the analyzer. And this will be connected to this point will be connected. So basically each this point, these two different points will be connected. This will be connected to source, power source. This will be connected to the converter or the equipment which is under test. So in between this power source and the converter, this network will be present, and this network will give us different noises. Now if I have to draw the circuit diagram for dual LISN, so it will be the similar, only thing is that two, like everything will be twice. So basically there the positive and the negative points are connected separately. So we'll be having the similar inductance. So this is with respect to positive line, and then obviously this similar capacitance will be connected, and that connection is to ground. So this ground line will be coming in between. So you can see here, so this basically ground line which will be coming in between. Now here this 0.1 microfarad capacitor will be there, and again this like resistance with respect to this will be there, and then here the same capacitance will be connected here. This is 1 microfarad, this is 50, and this will be connected to negative line. Sorry, here one inductance will also come. Same inductance like positive line, it will be connected here, right? Again here the resistance and the this capacitance will be there, and this will be connected to 0.47 microfarad. Okay, this is with respect to the dual realization. So this point generally goes to the 50 ohm termination. So here I am just showing it 50 ohm to this. Okay, so this is how the network looks like. So single and dual realization. So this network we need to use for the measurement. So yeah, more about this I'll be discussing in the next class. So different other noises, how it looks, and what is the level of attenuation, or what is the limit that is provided for EMI noise, and how to design filter. Okay, so that I'll be discussing in the next class. Thank you. So just a minute, these are the references you need to refer for this lecture. Thank you.